Hey everyone, Akil from Oxford Academy here. This is part 4 of our related rate series, and today we're going to be talking about the streetlight problem. So let's get started. Jason walks towards a 24 feet tall streetlight at a rate of 5 feet per second. If Jason is 6 feet tall, how fast is the length of his shadow changing? So let's go ahead and interpret this problem with the diagram as per usual. So, streetlights are typically vertical, so I'm going to just indicate that with a vertical line. With this right here is a length of, let's say this right here is a length of y, which is 24 feet. And this right here, let's call this the ground, all right? All right, let's call that the ground. And let's go ahead and just sort of try to find a geometric shape that we could sort of use as a tool. And that right there is just gonna be a triangle. And I'll show you how we can use that. So we have y equals 24 feet. This is just the total this is a total scenario. Let's go ahead and add in Jason. So let's go ahead and put Jason right here. So this is Jason. His height is 6 feet. So let's call that h, which equals 6 feet. And this right here is the length of his shadow. And this is the distance Jason is from the streetlight. So let's go ahead and call this distance right here x, and this distance x sub s, and we know that he moves at a rate of dx dt, which is equal to not 5 feet per second, because notice something. If he's moving towards the streetlight, this distance right here, x, is decreasing. If it's decreasing, then this dx dt right here must be negative. So this is negative 5 feet per second. So let's go ahead and try to find an equation that sort of relates these quantities. So notice something here. If these are vertical and this is a horizontal ground, that means that these are both right angles. And let's also go ahead and draw in an angle right here. We'll call this angle theta. If you notice, this angle theta is shared between the two triangles. If we have two angles that are the same in a triangle, that means they have angle-angle similarity. So these triangles are similar. So let's go ahead and use a trigonometric ratio with this angle theta to get a relationship between x and x sub s. So let's go ahead and try using cotangent here. So cotangent theta, this is going to equal x sub s over h, which is 6 feet. That does not change. And this right here is going to be equal to this total length right here, which is actually x plus x sub s, and all divided by this total height right here, which is 24. Now what I have to do is we just sort of have to cross multiply. So 24 x sub s is equal to 6x plus 6x sub s. And solving for x sub s, moving all the x sub s terms to the other side, this gives us 18 x sub s equals 6x. And isolating x sub s gives us x sub x equals 1/3 x, because 6 divided by 18 is 1/3. Now all you have to do is do our implicit differentiation, or ddt. And this is actually really simple, because the derivative with respect to time of x sub s, implicit differentiated, that's going to be dx sub s dt. And this derivative right here is going to be 1/3 times dx dt. And we know that dx dt is negative 5 feet per second. So this gives us dx sub s dt. This is going to be 1/3 times negative 5, which gives us negative 5/3 feet per second. So what does that mean? That means that the length of his shadow is decreasing 5 feet every 3 seconds, or 5/3 feet per second. That's how fast it decreases. So yeah, that pretty much sums up the streetlight problem. This is Akil from Oxford Academy signing off, and I hope to see you in future videos.